In the first part of this video on object concepts, we will discuss the fundamental characteristics of object-oriented languages and provide a simple example of a program that uses two objects of a class that we define. We will begin this discussion by an overview of object-oriented languages, discussing what features are required for a language to be object-oriented, and explain the benefits of using such a language. Java meets the requirements for being an object-oriented language. So let's consider what characteristics a language must contain to be considered object-oriented and what features of Java correspond to each required characteristic. The first requirement is that a language provide a mechanism for encapsulation, which means grouping together the data representation of an object together with the operations that can be performed on it. Java classes provide this mechanism by grouping together instance variables and instance methods. The next requirement is that there be a way to hide information, which means restricting the scope of the data representation of an object. In Java, the private modifier makes it possible to restrict the access to the instance variables of a class to only its instance methods. The final requirement is that the language provides syntax to support inheritance, polymorphism, and dynamic binding. We will defer explanation of how Java provides these capabilities to the next video. It is equally important to understand what motivated language designers to incorporate features into modern languages that make them object-oriented. The first of those reasons is to reduce the cost associated with making changes to the representation of an object. The Y2K problem was a classic example of the high cost of changing the representation of a year from 2 digits to 4. It pertained to programs written in a language that was not object-oriented, COBOL. Because the representation was exposed to whole programs, every line of those programs needed to be examined for potential modifications. In Java, provided the instance variables are made private and no changes are made to the method's signatures, the only portion of the code that needs to be examined when the representation changes are the methods of that class. The second benefit of using object-oriented languages is that larger reusable modules can be created. Rather than having just a library of general-purpose functions, object-oriented languages have libraries of reusable classes. Java has a number of reserved words that affect the visibility of both the data and methods. Initially, we will consider the two most fundamental modifiers. So let's consider the difference between these two modifiers. When the modifier public is placed on either the data or methods defined in a class, those names can be accessed anywhere within the program. By contrast, using the modifier private means that those names can only be accessed within the class in which they are defined. It is important to follow best practices in using these modifiers. Because instance variables define the representation of objects of a class, to ensure that the representation is hidden from other classes, instance variables should always be private. Methods of a class are usually intended to be called by methods of other classes. For that reason, they are most often declared public. We should note, however, there are times when we might choose to make a method private, if it was created to factor out common code needed by other methods of the same class, and it is not intended to be called from outside the class. Constants are different from variables because they cannot be changed. For that reason, public constants are acceptable if the expectation is that other classes will need access to them. If not, making them private is fine too. Next, we consider constructors. As their name suggests, they are methods that are used to create objects of a class. But they differ from ordinary methods in several ways. First, programmers are not free to choose their names, which is true of any ordinary method. Instead, the name of constructors must be exactly the same as the name of the class. Next, unlike ordinary methods that must have a return type, constructors cannot have a return type. It is understood that what they return is a reference to the object that they create. Finally, constructors are called in a different way. The call to a constructor is always preceded by the reserved word new, that is a request to dynamically allocate memory for the object. One final point about constructors that is important to understand is that when the programmer provides no constructor, the compiler will supply a default constructor, which is one that accepts no parameters. If any other constructor is provided, and a constructor with no parameters is needed, it must be explicitly provided. We conclude the first part of this video with a classical example of a class that illustrates object-oriented design, which is a bank account. Like all objects, it requires instance variables to define its representation. An actual bank account would need numerous instance variables, such as the account number, the customer name, and so on. To keep things simple, we have included only the most fundamental variable. It is the balance, which is, of course, how much money is currently in the account. Next, we consider the operations that can be performed on such accounts. The first is the ability to deposit money into the account. The second is to withdraw money from the account. The third is the ability to transfer money from one account to another. The final method returns a string that contains the account balance, which enables us to display the amount of money that is currently in the account. You should note that although with the display method we have essentially provided a method that gets the balance, providing one to set the balance would be a very poor design. A bank would certainly not be in business for long if they allowed its customers such an ability. Some textbooks encourage the practice of providing a get and set method for each instance variable. We regard this as a poor practice that violates the spirit of object-oriented programming. When the methods mirror the representation, changes to the representation are more likely to require changes to the method's signatures, which is the very thing that the object-oriented approach seeks to avoid. Now let's look at the code required to implement the class. Note first that the instance variable balance has been declared private. Next is the constructor that copies the starting balance provided by the client to the instance variable balance. Initializing instance variables is what constructors most often do. The deposit method adds the amount being deposited to the current balance, and the withdraw method subtracts the amount being withdrawn from the current balance. Notice that we are allowing overdrafts, mainly to avoid complicating this example. Scrolling down to the remaining methods, the transfer method is next. It is different from the previous two methods because it requires two accounts, not just one. So the second account, which is the account that the money is being transferred into, must be passed as a parameter along with the amount. To avoid duplicating code, note that we accomplished this transfer by calling the existing withdraw and deposit methods. Take note also of the fact that when the withdraw method is being called, we do not need to specify the account because it is being withdrawn from the same account on which this method was invoked. The compare-to method of the string class, with which you may be familiar with, is structured in exactly the same way, since it too requires two objects. The display method is the last one. It is used to display an account object. It simply returns a string containing the value of the balance preceded by a label. By itself, this class is not a complete program. We need a client class that makes use of it. And that class needs to have a main method. The account main class serves that purpose. It is a simple driver that contains calls to each of the methods for the purpose of testing the class. First, notice that we have created two account objects, a checking account and a savings account, which have been initialized to contain starting balances. We next call the deposit, withdraw, and transfer methods to test them, and then display the final balances of both accounts to confirm that the balances are being properly updated. Finally, let's run the program. You can check the output to confirm that each of the operations is being performed as it should.